Now that we know what the distribution of the sampling process for proportion would look like, we're now going to use that information to come up with a confidence interval for a population proportion. So again, we're going to talk about how to obtain a point estimate for the population proportion and how to construct and interpret a confidence interval for the population proportion. We will not determine the sample size for estimating that. It is in the textbook if you would like to know. A point estimate is, again, a value of the statistics that estimates the value of the parameter. If we're working with a proportion, then the point estimate is the sample proportion, which is, again, the number of individuals in the sample with a specified characteristic over the sample size. As an example, a Quinnipiac University poll asked 1,783 registered voters whether they favor or oppose the death penalty for persons convicted of murder. 1,123 were in favor. A point estimate, then, would be 1,123 out of 1,783. The number with the characteristic we were interested in, those that approved of capital punishment, out of all those that we surveyed. So we ended up with 0.63 as our estimate. It is a point estimate because it's based off of this one sample. Just like we could do with the population or with the population mean and come up with a point estimate using the sample mean, we're able to come up with a point estimate for the population proportion by looking at the sample proportion. And in a similar manner, we can construct a confidence interval. A confidence interval for an unknown parameter consists of an interval of numbers based off of the point estimate. Instead of looking at this one value, we're going to try to come up with a range of what we think the population proportion might actually be. The level of confidence is the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained, and it's denoted by 1 minus alpha 100%, same as it was before. Alpha is a level of significance that we choose. 1 minus alpha is then the level of confidence we have in our process. As an example, if we chose a level of significance of 5%, we would have a 95% confidence interval. So a 95% level of confidence has a 5% level of significance. And the confidence interval is, again, a point estimate plus or minus a margin of error. How we come up with the margin of error for the proportion is going to be a little different than what it was for the mean. Okay. The margin of error will depend on the level of confidence that we've chosen, the sample size, and the standard deviation of the population. The more spread there is in the population, the wider our interval will be for the given level of confidence. For the sampling distribution of the population proportion, we know that the sampling distribution will be approximately mean or approximately normal with a mean equal to the true proportion of the population and a standard deviation of p times 1 minus p over n, provided that np times 1 minus p is greater than or equal to 10, and that our sample size is less than 5% of the total population. Just like with the sample mean situation we had, though, we're not going to know what the true population proportion is. If we knew that, there'd be no real sense of taking the sample and coming up with a sample proportion. The sample proportion, however, is the best estimate we have currently of what the population proportion is. So in finding an estimate for the population standard deviation, sigma sub p hat, if we change all these p's to p hats, that would be the sample proportion standard deviation, which would be S sub p hat. Okay. And we would then use that sample estimate to come up with our standard deviation value. We're still going to have a lower bound like we did before and an upper bound, except now we're going to use a z-score instead of a t-score. We'll use z alpha over 2 instead of t alpha over 2. The sample size here will be sufficiently large so that we can use the normal table rather than the t-table. With population proportions, we will use the normal table rather than the t-table. So an interpretation of the confidence interval is that we are, however, confident that our interval will contain the true population proportion, which means that if we were to do this over an infinite number of times, about this percent of the intervals would contain the true population proportion. Just as before, the true proportion will either lie in our confidence interval or it won't. So there's no probability it lies in the interval. The confidence comes from the methodology that we're using to construct these intervals. That over a long-term process, the majority of the time, we would capture the true population mean. The margin of error in this case is how much we're adding on to that population proportion, or excuse me, that sample proportion. And it's z alpha over 2 times the square root of p hat times 1 minus p hat over n. So let's go back to our capital punishment example and construct a 90% confidence interval for the true proportion of registered voters who would be in favor of the death penalty for persons convicted of murder. Well, we know that the population, or the sample proportion that we came up with was 0.63. If I take the number in the sample times that sample proportion times 1 minus that, it's more than 10. The sample size is certainly less than 5%, so we can assume that this distribution is going to follow a normal curve. If I look up alpha equals 0.10, the z alpha over 2 for that is z sub 0.05, which is 1.645. Again, why are we using 0.05 and not 0.1? Well, remember, we wanted a 90% confidence interval, so we want the middle 90% of that distribution, which means we're going to leave 10% outside of that middle 90. That 10% is split up as 5% on the left and 5% on the right. We can get a value of 1.645 for our z value. There are a couple ways that you can come up with that. One would be to go to the normal table and look inside the body of the table until I came up with 0.95. It'll actually be easier to go to the negative side and look up to how I could come up with something as close to 0.05 as possible. And notice that happens halfway between these two. So I notice that's at minus 1.645, and I could come up with it that way. Or I can go to my t-table. Remember that the t-table approaches the normal as the sample size gets bigger. So the infinity row down here represents the values from the normal table. So if I look at this infinity row, that will give me those critical values that I will need to use for my confidence intervals. So I'm going to do the infinite row. I know I want the 0.05 column because I want 5% in the tail, which tells me 1.645. So that's where the 1.645 comes from. And now we'll get back to our formula that we were doing. So I know that Z is 1.645. I know the sample proportion is 0.63. We're going to plug that into the lower bound and upper bound formulas. So that's going to give me a lower bound of approximately 61% and an upper bound of approximately 65%. So we can be 90% confident that the true proportion lies between 0.61 and 0.65. Again, that does not mean there's a 90% chance that that contains a true proportion. It means that because the true proportion is either in there or it's not. It means we're 90% confident in the methodology that we have done that we will have captured the true proportion. Well, that concludes our discussion of confidence intervals for a proportion. It's not much different than what it was with the mean. We still needed a lower bound and an upper bound. We still had to take a point estimate and add and subtract some margin of error. The difference was that the point estimate was the sample proportion. The margin of error was based off of the standard deviation of the sampling process for the population proportion, which was the square root of p hat times 1 minus p hat over n. And we used a z value. We used the normal table rather than a t value. Or equivalently, we used the infinite row in the t table to come up with the z value that we used in our formula.